Cuando guste.
¿Ya está la transmisión?
Sí, ya.
Okay. Well, it's time to continue with our international conference on electrical engineering, computer science, and automatic control. This is the mechatronic session. So we are start with the first talk will be modeling of electric trains for power system dynamics analysis. It will be Jose Emilio Cerón Guerrero. Please will be giving our talk.
Donde guste.
Good afternoon, everyone. Thank you for joining us. Today I'm going to talk about power system and electric trains and an issue that we have here in Mexico. Basically, I will cover a small introduction about this issue, a description of the power system that we have in Mexico, the rail system model that we have some concerns to face off, and some simulation results about the co-simulation of both systems. And then brief conclusions. So let's talk first about the introduction. Those who are from Mexico maybe have heard about the Tren Maya, which is one of the main projects of infrastructure for the Mexican government. And it's a large project. Well, it's a large project that covers most of the peninsula. And it's a project that is a project in railway terms. It covers okay. So it's a project that covers most of the peninsula, but it has great nature. Most of the tracks are only operated by diesel. That means that the trains can operate by diesel or connected to the electrical. But about almost 700 kilometers are operated connected to the grid. So this interaction with the grid will be important for this network. And we can see in the other side the network that we have in the power system. Although the region is very large, we have to be clear that most of the load is concentrated in this area and this area, which are the main economic regions in this peninsula. So that makes a little bit the difficult operation of the grid system, because most of the system behaves like we call it a radial system. And that generates some instabilities with the control. So let's talk first about the power systems and the particularities. Almost all of the Mexican grid is interconnected from the north area to the south, except with the Baja region. So it's a very large system with thousands of nodes and transmission lines, power generators. But there are two main regions that are radial or equal radial, which means that the controls have some issue. One is the region that is the northwest region, and also the peninsula region. These regions are the most challenging areas for us to operate. So when we have a train in this area, it's more challenging for the same reason. For example, those who live in Mexico know that we have a couple of trains here, and because the network is strong in that area, we don't have any issue with those. So simulate the whole system is difficult. So we have got only the peninsula region to interact with the train Maya. So this interaction is made in 7 points that are called sets in Spanish, which basically are the traction substations that we have for this system. The peninsula region is divided in 8 zones. Basically, The first one is Chetumal, the second one is Campeche. The third one is a special region called Ciudad del Carmen, Ticul, Mérida, Tizimín, Motul, Cancún, and Rivera Maya. As I mentioned previously, Rivera Maya and Cancún are the main load centers. We have some generation in this area, some generation in Mérida, but this region have the particularity that there is not enough energy produced in this region. We have to bring the energy from the rest of the country. Sometimes about half of the energy consumed in that area is imported, but it's imported only by for power transmission lines. That means that it's a very fragile system in terms of stability, and we have to make all the analysis to make sure that any infrastructure that we add to that network works well and don't generate any new issue. So I modeled all the region, all the region, including its zone. An example of one of the zones. This is Chetumal zone, one of the smaller ones. The region was modeled in EMTP, which is a software for electrical simulations, with power generators, loads, all transformer, transmission lines, and so on. So it's a large model for the power system. And also each, for example, each generator have a more detailed control. For example, this is one of the synchronous generators. We have each transformer connecting to the network, the synchronous machine, and the primary controls. In this case, for example, we have a governor and for speed control and an exciter for the voltage stability control. So that's how I simulated our system. Now we have to include the rail system in the simulation. In the case of the train Maya, we have a system that is called 2 by 25 kV system. That means that it's powered by a substation that is connected to the grid, but also have some self-transformers that helps to reduce the voltage drop across the catenary system. So that makes it a little bit more difficult to include because it's more elements, more details that you have to have, and also more challenging because how much detail you include about the train system. You can have a very complete model, but it would require a very small time step, and the power system have a relatively large time step for the simulations. So I mentioned the catenary for this project is a double track catenary. And we have for one direction all the infrastructure and another infrastructure for the other direction. We have, for example, this is one portion of the system. We have the transformer, the main traction transformer connected to the grid on this side to the catenary, both catenaries, one for one direction and from that direction, and also the transformers that we have for the to limit the voltage drop across this catenary. If we didn't have these transformers in the middle, we will have require more transformers connected to the main grid. That's challenging because there is a lot of jungle. So it's difficult to build new substations and create environmental challenges for us. So basically, this is the system. We have included some, in this case, we have shown some trains, very high trains, and we included 20 trains in the whole simulation. And this is the same as diagram, but just in the PT version. So it's basically the same, just in the simulation how it looks. So you can also model the catenary system as you wish. You can have a very detailed model for the whole system. But the more detailed you are, the slower the simulation becomes. And there are some also issues with the numerical stability, because one of the problems that trains move along the catenary system, the position is not fixed. So you have to be calculating the change in resistance and inductance as you move through the catenary. To avoid that calculation, we made a simplification that we divided the catenary system 1 kilometer section. And that way, only we assume that the train is moving, but 1 kilometer by 1 kilometer. It's not the idea, it's like a steps. That is not the reality, but the result doesn't change too much and gives a lot of the numerical stability for our simulations. So that's why we make it. In that case, we represent the catenary with the simplest model, just resistance and inductance. We calculated the inductances between catenary, the rails and the returning feeder, but that number was not too high, so we decided to ignore them for this first iteration, and also the capacitive effects between all those conductors. So that's the representation in the software. Each section is 1 kilometer, and we have 690 sections. But the advantage is that if we modify one, we update the whole system. So basically, the detailed model of the train is like this. We have the 4-1 converter from one phase to the DC link bus. We have a node protection system, and then an inverter that is connected to the traction motor and this to the mechanical part. So that's a detailed model that we can improve if we will. But the problem is that it becomes very complex for each train. And remember that we have we are considering up to 20 trains at this time, so the solution becomes sometimes an issue. This is an example of a 4 megawatts train. We have 4 induction motors. These are the inverters, 2 inverters, each inverter supplying 2 induction motors in parallel. We have the rectifiers, 2 rectifiers for each system. And here we have all the mechanical equations represented to coordinate with the interaction between each of the motors. They basically operate kind of parallel. So this is the result that we have for the detailed system. We have result that we feel comfortable. But the problem, as I mentioned, is that this simulation takes a lot of time for one train. So if we include 20 trains plus all the network for the power system, the simulation will take ages. So we decided to simplify the system. So first we need to know how the power is consumed. How is the power consumption within the train? We have, for example, this, and we can see that there is some loads that are kind of static from the transient and the dynamics point of view, which are, although they are variable, they are kind of constant when the condition are right. And the other, the larger consumption of energy is for the tractive effort that we have for the train. So we decided to divide the model into these 2 areas. The losses are included in the catenary system. So for this portion of the power, we put a fixed consumption of power, and for this we include only a simplified version of the traction equations. So it's something like that. As I mentioned, we have a model for the train. There is also a model that helps us to move the train along the tracks. Basically, it's like a multiplexer that selects in which position of the track is the train. So, as I mentioned, it's also a multiplexer with a huge number of inputs and outputs, but it's The circuit have a lot of elements, but it's simple to solve for the numerical simulation. And also we have the simplified version of the train. We have one part that is electrical and one part that is mechanical. This is the electrical part. One node is connected to the rails, and the other to the catenary. And we have a fixed consumption of power, in this case around 400 kilowatts. And we have a variable consumption of power that will depend on the traction effort that is required to supply the train. It comes from the results of the speed of the numerical solution of the traction equation of the train. And basically, we only calculate the current that is required to supply the power at that velocity. So this is a solution of the mechanical equations. It's the second law of Newton. So it's a lot of forces interacting there, but it's a simple equation. So we made, as I mentioned previously, 20 trains that interact with the whole power system of the peninsula, and that was that we showed here. For other power systems, in power system we try to keep balance the three phases. We usually are kind of boring if you want to keep like that. But the problem with trains is that they are by nature single phase loads. So they generate an imbalance in our three-phase systems. And that's the main concept for us as a grid operator. We have to avoid the effects of these imbalances. In the case of the imbalances, the main concern for us is that they generate extra heating in all the elements that have magnetic cores. We're talking about the transformers in the power grid and the synchronous generator. And these effects are not instantaneous. I mean, they don't generate any instantaneous damage in our network, but they reduce the life of our assets. For example, a power generator can last between 20 30 years before it requires its major maintenance operations. I mean, they have maintenance for this. And in this case, it reduces the life to 5 years. So it's a large reduction of the life of the system. So that will reduce the imbalances. So here is the result of the voltage. We can see some imbalances. And the question is it bad or not bad for the system? We have some imbalances of the currents. The same question, is it bad or is it good? There are some criteria about this. And also the power that is transmitted from the network of the peninsula to the rest of the country. In the voltage, we don't see any imbalances at first sight. But we see some slight imbalances in the power transmitted to the other, but it's small. So in conclusion, we've made the calculations. We built more than 400 nodes of the power system, 19 synchronous generators, over 200 two-winding transformers, 7 traction substations, 20 trains, and we calculated the voltage balance factor. We estimated that it's less than 1%, that is the recommendation. So in this price iteration, the system seems good. But we have to further reserves if the other effects interact, if we are still okay. Any questions?
Thank you very much for your presentation. We have time for one question. Somebody? No? I know that there has been some problems at the peninsula with the blackouts. It is consequence of the Maya trains?
No, because some of the infrastructure is still under construction, and the trains are still working with diesel. they are still not fully connected to the.
It is no problem or robustness of the electrical network.
No,
No?
it was not the
Okay.
issue.
It is something that everybody said and it's pretty.
No, it's related because we're putting network. I cannot give too much detail, but basically the train is in this area and the issue is in this area. I mean, the issue basically is that there are only 4 transmission lines that connect the country with the peninsula. And that's an issue that has been run. It's more the lack of infrastructure that we have not invested to put more transmission lines in this area.
Okay, thank you very much. Let's. Okay, our next talk will be trajectory tracking and obstacle avoidance, a comparative study of LQR and reinforcement learning approach. Okay, on internet?
Yeah.
Okay, now I'm going to share my
Um,
PPC.
the audio is not working. Sorry.
Okay. I'm sorry. Did you listen me?
Yeah.
Okay, thank you so much. And now I'm going to share my presentation. Okay, now done. Okay, now you can say me if you say my presentation.
Yeah, it's all right.
Okay, thank you so much. Okay, hello everybody. My name is Juan Camilo Tejada Orjuela. I am professor at Universidad Iberoamericana in Ciudad de Mexico. And today I am pleased to present our work titled Trajectory Tracking and Obstacle Avoidance, a comparative study of LQR and reinforcement learning approaches. This research was conducted in collaboration between Universidad Iberoamericana, Universidad EIA, and Universidad EAFIT. These last 2 universities are from Colombia. And the focus of this study is comparing 2 motion control paradigms and omnidirectional robots. Okay. I want to start with my motivation and context. The first is that the motivation behind this work in the increasing of the use of multi-robot system in industrial and service environments, okay? And one of the most important things in this moment is that this system must navigate with dynamic and uncertain scenarios, requiring so many controls that are precise and adaptive, okay? The traditional controls like LQR and other classic control offer an excellent stability and efficiency, but so many times they rely on accurate models, okay? And in the other hand, we have the reinforcement learning, and this RL can adapt to unknown conditions, talk at the cost of higher computational demands, okay? Our aim was to systematically compare both approaches in control simulation setup. Okay, now we had 4 principal research objectives. Okay, the main goal of this study was evaluate and compare the performance of feedback linearized, LQR controlled, and a semi-gradient Q-learning algorithm. This for the trajectory tracking and obstacle avoidance. Specifically, we have development a discrete time kinematic model for a mechanical wallet robot. Second, a Q-learning agent using tile code function approximation. And third, an quantitative comparison under identical or semi-identical conditions. Through this, we had aimed to highlight the strength limitation and rate of bearing the model based at the learning based control. Okay. Okay, our robotic platform was an omnidirectional based cable equipped with mechanical wheels, each set of 45-degree angles. And this configuration allows a full autonomic motion. The robot can move in so many directions and rotate independently from this moment. And this is so important because it's have so many behaviors and so many capabilities over other structure mobile robotic structures that allow us to make so many different motions. However, with this system, we introduce a nonlinear coupling in the kinematics, making the control design a new challenge. And we had modeled the robot motion using standard mechanical equations, and we have made and we have obtained and discredited the model for both the LQR and RL controllers. This discrete time kinematic model can be observed in this film. That when we have do this, we want to simplify the nonlinear elements of our model to can be implemented in so many microcontroller systems. Okay. Our first approach was the reinforcement learning, and the reinforcement learning approach was implemented a semi-gradient Q-learning algorithm with type coding function approximation. The robot state includes its position and its orientation, while the action space consists of a forward motion and rotations. The reward functions penalizes the distant goal, the orientation error, and the collisions, promoting different elements like the inefficient and self-trajectory and trajectories. One of the most important elements is that we have do these elements with an state representation with the type code function. Okay, the action space was 3 elements with move forward, rotate clockwise, or rotate counterclockwise. This is the principal action that we have used for our reinforcement learning agent. And finally, the reward design was designed principally with the distance to the target, the heading error, and the collision with the obstacle. Okay, this allows us to encourage efficient collision-free navigation. One of the most important things is that we have we have to train our agent for the 3 different scenarios, because the agent learns the autonomous navigation principally based in the reward design. Okay, this was our parameters. The time step was 0.1 seconds. The learning rate alpha was 0.0625. The discount factor gamma was 1. The tiles per tiling was 8. The number of tilings was 8, and the independent runs was 10, and the episodes per run was 500. The maximum steps per episode was 500, and we was used these 3 models for the rewards. The first model of the rewards basically was based in the error. We made our error and we have calculated our differential elements to the final motion. We have made a penalization from minus 100 points open collision and boundaries, and 0 for rewards at the end of the episode. Okay, the second model for the reward was made for the scenario that we have so many obstacles in the systems, and we have added a new penalization from minus 1000 open collision and boundaries. Finally, we have made our third reward model, and we have made the same, but we have included a new weapons over the trajectory, and these weapons give give to the model or to the agent a new reward based in the number of the new weapons that the model can avoid. Okay, now finally, our RL simulation results was based principally in the three scenarios that we had planned. The first scenario was straight line navigation. Basically, we had learned to the agent to go to the one point to another one or to another point. We had made our train about so many 500 scenarios, but that we have seen is that about the 100 and half scenario we have the agent have found their model, and the convergence to the error has been so many good. Okay, the second scenario was the static obstacle avoidance, and this static obstacle avoidance just going to from one point A to one point B, and the first and the task was to go to the final point, but we need to avoid the obstacles. But the most important is that we don't have to go any intermediate points, because we just import the first and the end point. Okay, and the final scenario was the same that the second scenario, but we have included the new goal that we have to avoid, or we have to find three different waypoints to complete this route. This was so interesting point, because we have found that the model can be trained and can be used experimentally. And one of the most important things that we have found a good agent that can do this element and without any model based controller. This is just a reinforcement learning control, and this was the start point of our comparison. The performance metric about our reinforcement learning problem was the convergence after approximately 200 to 300 episodes. The training time was ever about 10 minutes for train, and the collision-free navigation achieved. And finally, the moderate runtime computational load, approximately 200 flow per step. And this is what's a good metric, but we think that this can be optimized, and the algorithm can be better trained to going this number more lower, please. Okay, the second approach and the second scenario was the feedback linearized LQR. In this moment, we have changed our paradigm from one non-model based control to one model based control, and this was so important because we want to know what can be the difference between use a traditional control based in model versus and new model control based and non-model control like LQR. Okay, like RL model. For this element, we have used a traditional LQR based in nonlinear model. We have made a linearization based in feedback linearization. And finally, we have made the design of LQR, and we have obtained a model for the wheel velocities that can give us the possibility to give to the robots the possibility of to navigate into one planar state. For this approach, we have made just the scenario to go to point A to point B, because we need to combine another methodology of control to can avoid obstacles. For example, the exponential model based in parabolic models to avoid obstacles. Anyway, okay. And finally, we had made the experimentals to LQR for two scenarios. The first scenario is just going to point A to point B and made a trajectory. This was just a point to compare the benefits to use the reinforcement learning and the benefits to use the LQR traditional control. But the most important is not the individual results, because this was a good study. This was a good investigation to our understand why we have to use the LQR for any application and why we have to use the new based in no model controls like RL reinforcement learning or machine learning or anybody of these artificial intelligence models. And one of the most important things in this place is not the use of the tool, is the accuracy in the adequate selection of the control. Okay. Our performance highlights about the LQR was a steady state error lower than 1 centimeter. The computational efficiency meaning that 30 flops per step, and this is one parameter of comparison between the reinforcement learning and the LQR controller, and the real-time feasible of embedded hardware. The zero training time, immediate deployment, and the smart control effort, no aggressive maneuvers in the process. Okay. If we can, then we have made a comparison between the two scenarios and the two controllers, not based in the specific task, most in that each controller allow us to do with their use. Okay, the first element was the precision that we have that we have observed is that the precision of the LQR is higher than the Q-learning. The second is the adaptability. In this point, the Q-learning allow us to make so many elements and with a new training, and it's so many easy to change between one scenario to another scenario. We don't have found this versatility in the LQR and yes, in the model, in the artificial intelligence model. Okay. The third was the computational efficiency, and the LQR was about 30 flops in the execution, and we have about 200 flops in the reinforcement learning execution. And finally, the setup simplicity. We have found the setup simplicity of the LQR is so many high. We have observed that is so many easy to implement, but the reinforcement learning have so many of new conditions to can implement in real time. Now we have found a new objective in make this in real time, and we think that is the don't is so too easy to change or to make this implementation. Okay. Finally, if we can do a comparison with these two techniques, we have found that the Q-learning have approximately 10 minutes in offline to train, and LQR have a closed form in milliseconds. So we have found the solution in milliseconds. Okay. The steady state error in Q-learning is lower than 2 centimeters. In LQR is lower than 1 centimeter. The control efforts is high during learning, stable post-convergence, this is more important, and the LQR is low. Finally, the online computation is approximately 200 flows per step to the Q-learning and approximately 30 flows per step to the LQR. And finally, the adaptability. The adaptability was high to the Q-learning. We have an easy way to change within the scenarios because this model is a model free, because he just used the reward to use or to avoid one new task. Finally, to the LQR is limited because we need to a model to can do a good LQR to make our control or our mobility control. Okay, our conclusion was principally a systematic comparison was conducted between a model-based controller, a feedback linearized LQR, and model-free method, semi-gradient LQ learning, for motion control and an omnidirectional mechanical robot. Okay. The second was the LQR achieved high precision, low steady state error, and minimal computation, making it ideal for real-time embedded application and predictable moments. Okay. The third was the Q-learning required more training, and this was one of the fails that we have found. And computation, but demonstrating superior adaptability. Final, the K-insight. This is one of the principal elements of our study was we don't have an universally versed controller. Okay, this is one of the most important things that we have found in these elements. But the optimal choice depends about the environmental complexity and computational resources. This is so important because this study was the start of a project that now we are executing in multi-agent systems, and we have found that the possibility to combine in different layers of the control, a basic controller like LQR, and specifically in any moment of the trajectory of the movement, we can switch between an LQR control, for example, in L model pre-trained, okay? And we can use so many different hybrid systems to make these new elements based in these new algorithms, okay? The future is hybrid. This is the most important element. We have found that the capacity of make a new hybrid system give us new and best paradigms, okay? We have three principal steps, future steps: the real-time hybrid architecture that now we are now in this day we have implemented a hybrid architecture, the physical platform validation that this is one of the elements that we are doing now, and finally the deep reinforcement learning for edge computing, how we can take this reinforcement learning training to make it and to implement this in real time. This is really the new task or the new goal that we are searching in our investigation. Okay, this is the reference, and thank you so much.
Okay, we have time for one question only. Somebody there? From the mechatronics? No, nobody? Okay, how did you get the discrete model? I was not.
The QUER or the reinforcement learning model?
No, for the mobile robot.
Okay. No, the mobile robot was obtained principally based in the equations about canudas and the width, and based in the type of wheels. We have obtained the traditional model that was based in the rotation matrix and the geometric characteristic of the robots, and this model is nonlinear because we have cosines and sines and sinus.
But the discretization is just an Euler discretization, or it is an exact discretization?
This is an exact discretization. We have this H matrix based in the angles, and this H matrix is based in the Jacobian of the robot and in the velocities in the wheels of the model. Then we have, if we have the Jacobian and the velocity in the model, we can linearize with the model with the feedback linearization, and when we obtain the feedback linearization of the model, we can implement or we can transform with the model to a discrete time cinematic model to implement in the microcontroller directly, because this was the finally of the discretization is to implement in the Japan robots that we have in the university. Then we have to do the work to make this discretization from the simulation to make so easily the implementation in this work, in the future work.
Okay, let's finish the question.
Okay, thanks so much.
Now our next goal will be construction and characterization of a tendon sensor driven continuous robot.
Hi everyone, my name is Alan Coronado from the Centro de Investigaciones en Óptica AC. I'm very happy to present my project called Construction and Characterization of a Tendon Sensor Driven Continuum Robot. This project was developed at the Laboratory of Perception and Robotics, LAPIR, in CEO, in collaboration with the Instituto Politécnico Nacional, la Universidad de Ibero, la Iberoamericana, y Texas A&M International University. It focuses on the design of a soft robotic arm that can sense itself. A lightweight, retractable, and flexible manipulator inspired in nature. Nature shows us that the movement doesn't always need rigid joints, like in this robot. Think about on an octopus or a snake, how they move smoothly and adaptably. Now think about a turtle, how it retracts its neck, soft, flexible, and precise at the same time. Now think about in robotics, we call these systems we call these systems continuum robots. They can operate safely in unstructured environments without rigid joints. They can, and as we can see in the figure 1, this is the Nero 1 known robot with rigid joints. And in the figure B and C, we have two kind of continuum robots, pneumatic with they activate in pneumatic systems and tendon driven. Now, the arm is made of two sections, section 1 and section 2. Section 1 in blue and section 2 in red. Each one is controlled by 3 tendons spaced 120 degrees apart. Inside, there is an helical spring that works as a flexible backbone, this one. And the tendons are routed through 3D printed PDA and TPU links, and they are pulled by 6 DC motors in the base of the robot. This configuration allows smooth bending, retraction, and elongation. And you can ask, why 2 sections? That's because we need the independence of these movements. The first sections can move independently, and the second section at the same time moves independently of the first section. But here comes the big question: how can a robot with no joints, no dispositions? Our idea was simple. With the ESP32S3, we moved we sent signals to this driver, and this is the main how can I say it? I make that the tendons sense the large of the robot. So the tendons are sensor at the same time. Each one have a independent circuit to sense the distance of each sensor. And the ESP32 excites each section for only 50 milliseconds the impulses. to avoid heating because the tendons are made of nichrome. The nichrome is a resistive material that changes its electrical resistance when it stretches. This is a video of the prototype. Now we see the links, gripper, and this is the springs. There are 2 springs. This is the motor holder and the motors. Now we see the base. As I mentioned, it is made of 2 independent sections separated by a rigid flexible house. This one is the separation of the separator of the sections. And this is a test of the movements. And you can see the retraction and how it can move in the space. And the next one is the meditions of each one of the tendons and the movements of the robot. Now, to describe the arm mathematically, we use the constant curvature model, which assumes that each section bends like an arc. By using the 3 tendons length of each section, we can calculate the radius of curvature, the bending directions, and the spatial position of the arm tip. These equations connect the electrical measurements to the physical configuration of the robots. As you can see, the simulation give us the position of the tip only in 1 section. And now you can see the simulation of 1 and 2 sections. You can see that you can note the independence of the sections, section 1 and section 2 in red. The section 2 moves moves independently, and it has the movement of retraction, and as you can see, they spin, and we can know in every moment the position relatively of the to the base to the tip of the robots. This is a validation of the movement. We create a simple trajectory. You can see to this point and to this point. And by using only the data from the tendons, we were able to reconstruct the shapes you see above. This means the tendons are sensing correctly and the kinematic model is valid. This is a trajectory test. In another test, we commanded the robot to move toward a target. Using a simple controller, the robot reached the desired position with an absolute error of only 0.26 millimeters. And that's the trajectory test. As you can see, is valid for the project, and we have some conclusions. Our work presented the design and experimental characterization of two section tendon-driven subcontinuum arm. And what makes the system unique that the same tendons used for actuation also serve as self-sensing elements, providing millimeter level proprioception without the need for external cameras or sensors. the tendons intrinsic sensing have a solution of plus 1 point or plus or minus 1.48 millimeters and root mean square error or 1.19 millimeters. So in the closed loop test, tip errors stay below 3 millimeters, reaching 0.26 millimeters in representative trajectories. These results open the door for future integration with advanced control algorithms and effector actuation for real-world manipulation tests. And this is the main develop and thank you. And any questions?
No question, please. Okay.
It was not very clear how do the tendons work? Are they attached to the motors or how do you make the elongation of the tendons?
The motors moves the tendons.
Like pulley?
No, it's like, how do you say? It's spin and
And the tendons
Pull?
go around.
yes,
Yeah, it's pulling the tendon.
yes, and the tendons have the resistive wire. And this wire is like uh, I characterize this wire like an sensor. It is like a length sensor, and that's the way that I know the length of the of each tendon.
Okay. And what kind of control did you use? Because you said simple control, but not a specified one.
Yes. And this kind of control is an Cartesian control, and there is simple, but as you can see, it's very good. Only knowing the length of each tendon.
We have time for one. Okay, Carol?
What about the dynamic effects? I mean, the inertial effects and the external load changes because of the gravity effects.
Oh, okay. This is other. Oh, I think it's difficult, but you can see I only use the kinematic model. I don't use the dynamics, and at this time it's very good. The control works very well, but the movement of that the springs do to the robot, there is significant. If you have a robot like in maybe 4 sections, you will have a lot of moves in the tip of the robot, and that's why you to the in the future we need to move the robot using the dynamic model, and this is our kind of uh, of mathematically models, but it can be interesting.
Last question. It seems to me that your model is just an approximation of the kinematic one because of the complexity of the controller, of the tendon and so on. But you think that the approximation, I mean, the accuracy of the movement of the robot could be improved with another model, of course.
Yes, it can be improved. At this time, this model only knows the length of each tendon.
Okay.
This is that I can improve, make better the model in to other way, but at this time it's like an approximation as you said.
Okay, let's finish the presentation, please. We are going to continue with the analysis and control of the S3 of a serial spherical grids with balance links that it is on the internet.
Okay. Good afternoon. The topic I will present is analysis and control on ISO3 of a serial spherical grid with balance links. Introduction.
The presentation is not seen.
Okay.
Please, can you?
Okay. My name is Jessica Guadalupe Sierra,
Uh,
and the university.
It's still not sharing the PowerPoint.
Okay. Yes. Can you see?
No.
One moment.
Okay,
Can
it's
you see?
working right now. Yeah.
Okay. Okay. Good afternoon. The topic I will present is analysis and control on ISO3 of a serial spherical grid with balance links. Introduction. Compact and dexterous in manipulation is a fundamental requirement in modern robotic systems, where spherical grids play a crucial role by providing 3 rotational degrees of freedom in a constrained volume. In fact, design and control of spherical grids play a key role in a wide range of applications, including surgical robots, laparoscopy applications, and industrial robots. Among the key features, spherical grids must have high precision, low inertia, and lightweight. All of these features require a thorough mechanical and control designs, such as the mentioned in 5. In this work, we present the design and analysis of several spherical grids and detailed kinematic, okay, on the time and kinematic and dynamical model, of it, which serves as the starting point of the proposal of proper control strategies of attitude. We propose the geometry of the links to ensure that K are balanced, that is to say that the center of mass on the axis of rotation of each link As we shall show, this is key for the analysis simplification. The kinematic model is based on grid theory, while the dynamic model is based on Lagrange equation. To address the attitude control of the n effector, we transform the dynamic model initially obtained in joint space into tag space coordinates. Since the spherical grid rotation belongs to SO3, the special orthogonal group, we leverage control strategies formulated on SO3 described in the literature. More specifically, the proportional derivative PD and a light mode based control algorithm present in 8 and 9 respectively. The light mode control algorithms obeys the need to address ¿dónde está esto? To address potential perturbation appearing in the actor's input channel, which standard PD controllers cannot compensate. It is worth mentioning that, in contrast to previous work where alignment control is used for attitude control of spherical grids, we rely on the work in 9. A particular aspect of the adopted sliding mode control scheme is the proposed class of sliding surface which corresponds to a lead subgroup. Okay. It is worth mentioning that the main objective of the project is to present a dynamic and kinematic analysis, as well as the selection of an appropriate control for stabilizing mechanisms when a disturbance is encountered. The practical select for this application was spherical grids with balanced links. The decision to select spherical grids was made due to its importance in industry, as it is widely used in most robotics arms today. On the other hand, the control used in the project were proportional derivative control and the sliding mode control, with which a comparison of graphs was made to observe how the results vary. Let's start with the explanation of the kinematic analysis and dynamical model of the spherical grid. The proposed sync of the spherical grid with balanced links is displayed in the figure 1. And the figure 2 shows the direction and magnitude of the screw in each joint. The origin is placed in the zero reference system at the center of the assembly for simplicity. Okay. Recall that the first control implemented to the spherical grid with any type of perturbation was proportional derivative control. And in the figure, we can see that is a good result since the reaches the convergence of the origin for the orientation without any problem. Okay. In the figure 3, PD control from top to bottom, the subfigure illustrates the components of the n-effector rotation matrix, the corresponding angular velocity, and the control signal. In the second and third subfigures, the blue, red, and black lines respectively corresponding to the first, second, and third components of the angular velocity and torques. Okay. But what happens if the mechanism presents a perturbation? Well, as we see in the other image, it cannot converge to the origin since the system present oscillation generated by the perturbation, which are more visible in the angular velocity figure and here in the angular velocity. Therefore, It is an unsafe system, and this type of control is ruled out for this application. Now the question is, what can we do now? Well, it's necessary to implement another type of control that, regardless of the disturbance, can help me converge to the origin. For example, we'll try a sliding mode control. As can be seen in the figure, the system converges to the origin, which means that the rotation matrix is equal to the identity matrix, which is what we call the origin in IS03. Now, the angular velocity figure no longer exhibits the oscillation in activity with PD control. This is because sliding mode control offers greater robustness to parameter variation and external perturbation. But do we know that implementing such a control involves the presence of a phenomenon called chattering? We see in the Turkey figure. Exactly. It is chattering in control. At this point, you might be thinking that this is very high torque. However, if we look at table 1, it presents the physical parameters used to obtain all the results. These were obtained directly for the design of the spherical grid, which is very small. What you see is that the units are in grams and millimeters. So the torque is actually small, as I know they use the same units. Conclusions. We propose the design of a serial spherical grid balance with counterweight. The latter is the corresponding kinematic and dynamical analysis, which was provided in detail. For this spherical grid, we took advantage control strategies framed in IS03 and used them to provide control algorithms for the orientation of the effector. Finally, what can we conclude from this analysis and implementation of the control? As mentioned above, the main idea was the generation of genealogy, taking the spherical grid as a practical example. However, show you the steps to follow if you want to analyze any other type of system. It is concluded that it is feasible to follow these steps to analyze any other type of system, since the results were satisfactory. And the main requirement was met when the system converged to its origin, regardless of the disturbance present. Therefore, the control system is stable and robust. Okay. Thank you. Any question?
Any question? What would be the advantage of using the SO3 approach with respect with the classical approach? I mean, just to model and take a study of the working space.
SO3 con respecto de los modelos clásicos.
For example, we selected sliding mode control because the grid dynamics are nonlinear. And subject to parameters uncertainties due to balancing and coupling effects between the joints. Compared to classical PD or PID controllers, it maintains accurate trajectory tracking even when the system is likely unbalanced or perturbed.
Okay, thank you. Another question? No? Okay, let's finish the presentation. So we have the last presentation.
Yeah, the
Yes.
last one.
Okay, the last presentation will be comparison of parameter estimation techniques in permanent magnet DC motors.
Can you see my screen?
Yeah, we can see it.
Thanks. Good afternoon to everyone. My name is Alex Castellan Perez. I am a PhD student from the Universidad Politécnica de Tulancingo. Today I'm going to present our work entitled Comparison of Parameter Estimation Techniques in Permanent Magnet DC Motors. This work is a collaboration with the Universidad Autónoma Metropolitana, Unidad Azcapotzalco. This presentation is organized as follows. First, I'll give a little introduction and explain the motivation of the work. Then I'll describe the parameter estimation techniques that we compare. After that, I introduce the mathematical model of the permanent magnet DC motor. Next, I focus on the development of the algebraic estimator. And finally, I'll show the results and the conclusions. Well, the permanent magnet DC motors remain one of the most really used actuators in mechatronic systems, mainly because of their high efficiency, simple control, and versatility. If we want to control this motor or design a load control based on the dynamics of this system, we need a knowledge of these parameters. But in some cases, there are unknown because the manufacturer don't provide us that information, or maybe the health of the motor is not the best and change in the use. This is when the parameter estimation techniques come useful. They allow us to estimate unknown parameters for measurements of the system inputs and outputs. Also, we can use it for monitor the system health. The challenge appears when the measurements signals contain noise, which is common in real systems. The noise can come from sensors, external devices, or maybe the other motors that is near of our motor. So in this work, we propose to compare three estimator methods under noise conditions. The first, the algebraic method, the second, extended camera filter, and the recursive least square. First, the recursive least squares minimize a cost function based on the error between the measured and the estimated outputs. It is easy to implement, but it's sensitive to measurement noise. Second, the extended camera filter. That is a Fourier extension of the camera filter. The parameters are treated as a additional states. Has the advantage the optimal estimation for Gaussian noise. And finally, the algebraic method. That is based on the operational calculus and integral operators. It does not depend on the initial condition of the systems, and it uses integral operations, and for this is filter the noise from the signals. There is an advantage. The primary magnet DC motor is second order, well-known second order system whose dynamics is represented by the differential equation in the left. The first equation represents the electrical dynamics, and the second the mechanical. This system is differentially flat. That means that all system variables can be expressed in functions of flat output and a finite number of these derivatives. In this case, the flat output is the angular velocity, denoted by omega, and here by y. For the recursive least squares method, we need a discrete time model. So we use a numerical approximation of the derivative to obtain the difference equation shown in the right. And well, to make the presentation shorter, I only focus on the development of the algebraic estimator. We start from the differential equation of the system that is in the slide anterior. And we apply the Laplace transform. When we apply the Laplace transform, this includes terms related to the initial condition, which appear as polynomials at the Laplace transform S. To eliminate these conditions, we differentiate twice with respect to this. After that, multiply by S to the power minus 2. After that, return to the time domain, apply the inverse Laplace transform. That gives us an expression like that is in the screen. And after that, we need to estimate three parameters in this case: gamma, lambda 1, and lambda 0. After we apply these steps, obtain only one equation. To generate linear system equations, we iterate two more times. And after that, we construct the linear system equation like in the right side. And when we solve it, we get the estimates of the parameters. For the simulations, we design a trajectory controlled based on the differential flatness. Excuse me. The reference velocity trajectories were generated using Bezier curves to ensure the smooth motion. Noise was added to the output signal. I mean the angular velocity. Since the velocity is also used for the feedback of the controller, the control input becomes noisy. We not count with statistical information about the noise, and there are not any filtering in these simulations to make the conversion between the methods fair. And he can with the control input signals and the motor speed. The signals clearly show the effect of the noise. We didn't include the armature current in this slide because it's not used for any of the estimators, excuse me. But it will also be affected by the noise. This figure shows the estimation results for the parameter gamma. Both the algebraic method and the extended camera filter give a very accurate estimate. The difference between the true value and the estimate is almost inestimatable. On the other hand, the recursive least squares method did not convert because the noise in the measurements. As you can see, that is increasing its volume. Maybe if with the simulation has interval of time larger, maybe going to, I don't know, 2000 maybe. Now I'll present the result for the parameter lambda 1. The algebra method shows a small estimation error, error about 5%. The Kalman filter starts with an error of around 25%, but in around the second 8 converts about the 15% error, and again the least square estimation keeps increasing and is not clearly converts to the an value. Now for the parameter lambda 0. In this case, the algebra method and the Kalman filter perform very well. Again, the least squares that doesn't converge because the noise affects the performance. In summary, the algebra method gives excellent estimation speed, accuracy, and robustness to noise. The extended Kalman filter provides a good result, but require more time and information about the noise characteristics to get a very approximation to the real values. And finally, the recursive least squares fail to converge mainly because they need a preprocessing or filtering stage. That would be for my side. Thank you very much for your attention.
Okay. One question, please. No? Okay.
In the case of this technique, if you increase the number of parameters that you are going to estimate, let's say about 10, obviously you need more inputs to keep stable the estimation parameters. Do you think that the results hold? I mean, the method will still be the best option, or we can see a better response from the other?
Excuse me, can you repeat the question?
Okay, if you increase the number of parameters that you are going to estimate, let's say to 10, do you think that still the algebraic method will be the best option, or you think that it will switch to another of the method?
Maybe not algebraic parameter estimation technique. We use integral. Maybe for this case, there is only 3 parameters. It's not has a computational cost too high, but if we increase the parameters, the system of questions is too big, and for 10 parameters is 100 elements. Calculate the integrals for all the elements is a high charge for any device. Maybe it's not the best for that case. Maybe in that case we use a Kalman filter for that. No use that how much operations.
Thank you.
Another question? No, so explain the presentation. This concludes our session. Thank you very much for the attendance. Thank you.
Thank you.